Hi guys, welcome to my channel. So today we are going to start a series of lecture videos which are going to be focused mostly on vector calculus. So we are going to begin our study of vector calculus by first having a look at vector functions, and then what is going to happen is we are going to define what vector functions really are, and then we'll move on to start a discussion on what are known as parameterized vector functions. So with parameterized vector functions, our goal will be to actually see how we can define notions such as differentiability and integrability with these kind of functions. You see? Otherwise, let's get to it. So the first is vector functions. We want to give out a definition of what exactly do we mean by a vector function when it comes to vector calculus. You see, so before we start the definition of vector functions, let's first have a look at the word function itself. So what do we understand by the term function itself as far as math is concerned? You will see that if we are to go back a bit to have a look at what we did in our first year mathematical courses, you will see that we had a look of functions back then, but the way we looked at functions was a little bit different from what we're going to be doing here. So in our first year courses, we looked at functions which were functions of this sort. This is what mostly freshman calculus was all about. It was all about the study of functions that take us from the real set to another real set. You see that? So if we can just have a look and study this representation that we have here, there is a lot that we can learn from it on how exactly things like function are constructed. You see that? So if you can pay attention, you will come to a realization that every time if you want to define what a function really is, at first you need something that is called a space. You see that? So a space in mathematics, it is not something that has the same definition as what we know in real life. You see that? Because in real life we have a different understanding of space, like this whole vast emptiness that surrounds us. We refer to that as space. But in mathematics, the term space actually refers to a much different thing. You see that? So in mathematics, a space is something like this. It refers to an idea of a world in which inside of it there are things that are called objects, and also besides having only objects, we have also what are known as operations. You see that? So there are objects that reside within that environment. There are also operations that these objects can make use of to combine to manufacture new things. That's what exactly a space is. You see that? So if you look at this function that we have looked at in first year, you will see also a particular space that they were working on. They were working on a space that is called the space of real numbers, in which the objects inside were just the real numbers. You see that? And inside this space, there were many different operations that one can define, things like addition, multiplication, division, and all many other different operations. But the way we define functions was that we only paid attention to the objects that reside within that particular space, and we just did not have a look mostly at the operations that also reside within that particular space. You see, so that's what we need most of the time to define a function. We need the existence of a space and an object. You see that? Once we have those, then we can see that whatever we refer to as a function is something that actually moves us from one space into another space. You see that? But in first year, what we really dealt with was just functions that were moving us from the space of real numbers back to the space of real numbers. Those is the nature of functions that we looked at back then. You see that? But now, in this lesson, we are going to look at different types of functions. We are going to look at some things that are known as vector functions. So the question that we would like to ask now is, what exactly are vector functions? You see that? What exactly are vector functions? So vector functions, by definition, are functions which we can denote either using an F with an hat, because that's how we usually represent an object, which is a vector when it comes to math or physics. So we'll still adopt the same representation of this kind of object. You see that? But now, this thing, since it's a function, it has to have a space or spaces that it works on. So a vector function is a function which works on the space Rn, and what it does, it takes this space Rn and it maps it into another space, which I will denote as now as V arrow. You see that? Where V arrow that we have just shown here is the space of vectors. You see that? So we are familiar with objects that are known as vectors. You see that? So what we know is we have different representation of these objects that are known as vectors. But all these objects that we call vectors, they actually belong to a bigger set of things which is called the vector space. Though we are going to formalize what we mean by vector space as we go to other abstract subjects like linear algebra. So for now, we are just going to picture big V with an arrow as the set of all vectors that so far we are aware of in physics. If you have taken some physics, those objects which are like this in 2 dimensions, 2i plus 3j, or at times in 3 dimensions, they can be negative I plus 5j plus 6k. So what we're going to imagine now is that big V is a space which consists of all objects of this type. You see that? While on the other hand, Rn just refers to n tuples. You see that? So Rn refers to n tuples. So what we mean by that is that if you have R2, which we refer to mostly as a 2-dimensional space, this is just the same thing as just saying an R crossed with R, which is the set of all terms of the form AB, such that both A is a real number and B is a real number, like that. You see, so we know that R squared just means the space of all coordinates in 2-dimensional space. You see that? With AB not equal to BA in this particular case. You see that? So when we refer to tuples, we're actually talking about things that are more like coordinates. You see that? And also when we talk about them in 3D, we have R3, which is also the same as R cross R, which is the set of objects which are 3-point coordinates, such that both A, B, and C belong to the space of real numbers. You see that? So that's what a tuple really is. So Rn that you're seeing here, it has the same meaning again. It means R crossed with R n times. Like that. You see? So what a vector function does is that it takes any of these objects, depending on which space we are working on. So when we are working on 2-dimensional space, it will be taking these kind of objects. You see that? When we work with n-dimensional space, it will take these kind of objects. You see that? But what it does is it takes that object and it outputs a vector afterwards. You see that? So that's what a vector space is. So it's more like a function which takes in some numbers, and then it uses those numbers to create a vector. You see that? So to try and actually give a geometric view of what a vector space really is, let's consider the two-dimensional space. You see that? Let's consider the two-dimensional space. So we know that R2 can be represented geometrically as follows. So R2 this is how it can be represented. It can be represented as a space which consists of all coordinates that resides within this Cartesian plane. You see that? So everything that lies inside this Cartesian plane, whether here, or even here, is what we refer, even along these lines that you see there, which we refer mostly as the x and the y axis, they make the whole of what we call R2. You see that? So a vector function is something which works like this. So a vector function is something which comes and takes a particular point, which maybe we can call AB. And what it does is, at that particular point, it installs a vector, which we can represent as some line with an arrow at that particular point. So that's what. So even here, if you take a point here and plug it in, it will produce a vector at that particular point. So that's how we can actually understand what a vector function is. So even in three-dimensional space, it is the same thing. It takes all the points in that particular space, and then to each point it associates a vector. You see. So that's how we can come to understand what a vector function really is. You see. So to put it in a more nicer language, in 2D, a vector function can be defined as follows. You see that? So a vector function in 2D is the function. So a vector function in 2D space is the function f with an arrow, which takes us from R2 and maps us to V. You see that? So that's what it does. And I can actually say V2, where V2 means two-dimensional vectors. You see that? That's what a vector function is most of the time in two-dimensional space. It is a function which takes us from R2 to V2, where V2 just simply means, so let me put this to show that this is not a power, meaning it takes us to two-dimensional vectors. So such that when you feed it a coordinate such as xy belonging to three-dimensional space, you get a vector you get a vector gxy I plus h xy j, like that. So that's how we can actually picture a vector function to be. And sometimes this can be written as new notation as just gxy hxy, using what is known as the v bracket notation for the representation of vectors. So that's what a vector function really is. It's a function which takes a table, and from that it constructs a two-dimensional vector. You see. So examples of such vector functions are as follows. So let's define the vector function fxy, which is 2xyi minus 3x squared j. So this is an example of what we call a vector function. So let's see now what exactly it does when we give it a point. You see that? So you can see now that if maybe you feed in the point 1, 1 into this, what happens? You get 2i minus 3j. And when you feed the point 1, 0, you can see that you get minus 3j. So which means we can see that to each point in space, it is always associating a vector to that particular point. So this is how we define a vector function in 2-dimensional space. You see. What about in 3-dimensional space now? What about vector functions in 3-dimensional space? How will we define them? You see that? So in 3-dimensional space, this is how a vector function is. So in 3D, a vector function is the function. So it is the function f which takes x, it is the function which takes us from the space R cubed to big V cubed again, which means it takes us from 3-dimensional tuples to 3-dimensional vectors, such that when you feed it x, y, z, it outputs g of x, y, z, I plus h of x, y, z, j, and l of x, y, z, k. So that's what it does in 3-dimensional space. So for example of such vector function is the function fxyz, which is defined as 3z squared I minus 4xyj plus 5z minus 1 k. So that's what vector function in 3D space is. So to each point in 3D space, when you feed it in, it outputs or it associates a vector at that particular point. So like for example here, if you come up and say, what is the f of 1, 1, 1, you will see that you get 3i minus 4j, then that's it. It's like that. So which means at this particular point, it will associate this vector at that particular point. So that's what we can say in general what vector functions are. So they are just functions which takes a set of real numbers, and from that set of real numbers, they manufacture a vector, you see. So that's where actually the term vector function is coming from. You see that? It means they associate a vector to each and every particular point that you feed to them, depending on the space that you are working with. Because what we call a space, it is a set of points that make up a space. You see that? So what it does is it takes each particular point, and to that point it associates a vector, where a vector can be visualized as some line with an arrow with the length of the line signifying magnitude and the arrow pointing to a particular direction. You see? So that's what we can say now about vector functions. So this is how we define them, and these are a few examples of them. So every time when we talk about vector function, this is what you should understand. You see that? So that's how we define them in 2D, and that's how we define them in 3D. Now that we have defined these, then we should now come to an understanding as to what exactly are we trying to do with this object. You see that? So the main goal of, if we were to go back to how mathematics is done, so we have seen that every time when I want to define a function, I need to have some spaces in which a function forms a bridge to move from one space to the other. You see that? But every time when we have functions, there are some things that we are always interested in. And one of those things is continuity, differentiability, and integratability. You see that? So this is what we want to head to now, to start bringing in such notions with these objects that we have already created here. But it will be a huge leap now to try and do or establish all these concepts using these generalized objects. So what we're going to do is we will start first at a level which is close to where we're coming from, because continuity, differentiability, and integrability is something that we have looked at in most of our freshman courses, where we looked at what are known as univariate functions, functions that only take one variable and also return a real number out of that, you see. So what we're going to do now is we'll try to see if there is a way of connecting such functions as these to what we already know, you see that. And in order to do that, we bring about what are known as parametric functions. You see that. So now in this section, we'll try to then introduce what are known as parameterized vector functions. You see that. So this is what we want to talk about right now, a parameterized vector function. So a parameterized vector function is a vector function that is nothing different from the vector functions that we have already introduced. But the thing about these is that these are vector functions that have been made to be dependent only on a single variable, which we call the parameter. Because already from what we've seen that most vector functions, they depend to a minimum on two variables or more, depending on the space that you are working on. You see that? So now, what happens most of the time is we always try to bring things to the level of what we understand, and then from that level now we can use the tools that we've already established to see how we can do a lot of things. And then we'll try to see now if we can then generalize whatever we have done to higher dimensions. So that's why now we have to bring in some parameterized vector functions. But what exactly is a parameterized vector functions? So we are going to define these also in 2D and 3D space. And then later we shall move these to higher dimensions, but now we'll just restrict ourselves into the 2-dimensional and the 3-dimensional space. So let's define these in 2D space, what they are. You see that? So in 2-dimensional space, a parameterized vector function is a vector function of the form. So it is a vector function of the form FRT, which is equal to xt yt, like that. You see that? So in 2-dimensional in 2-dimensional space, a parameterized vector function is a vector function which behaves only, or which depends only on the parameter t, in such a way that each of its individual components, the x and the y components, they are also dependent directly on the parameter t. So it is a vector function which is this structure. So examples of such vector functions are things like f prime of t is equals to cos 2t et. So this is an example of what we call a parameterized vector function. And in 3-dimensional space, a parameterized vector function is a vector function also of the form f of t, where x component depends on t, y component behaves of t, and z component depends on t. You see that? So an example of such a vector function is f prime of t is equals to 2t squared minus 1 cos 2t, then root of t minus 2. So all these are what are known as parameterized vector function. So a vector function which behaves only on a single parameter t. You see that? But if you look, you will see that what these things is, they take one variable, but in turn they retain a vector, which is either a 2-dimensional vector or a 3-dimensional vector. So that's what parameterized vector functions are. But having these kind of things now, it will allow us to actually talk about the notions of continuity and differentiability and integrability in the same way we did it in our freshman courses, you see, which is what we are going to see now as we move on with our discussion. You see, so first, it is good to be aware of what we mean by a parameterized vector function. So these are examples of what a parameterized vector functions look like. You see, so but one thing that you should take note of is that this is not time. So it is a good point to make, because people who study physics, every time when they see the small letter t, they always think it is in some way connected to time. So t is something which is not in any way connected to time. So when it is connected to time, we'll actually be specific about that. But this parameter can check any number. It can be any real number, either a negative real number or a positive real number. It is not in any way connected to time, because in our understanding of time, time is always a non-negative quantity, always starting from 0 and going in the positive direction. But this parameter can actually move both in the negative direction and in the positive direction, and therefore it is not in any way time. You see. So now, having these objects in place, now we'd like to see if we can actually talk about all the things that we do talk about when we're talking about univariate functions. And the first and foremost thing that we want to look at is the evaluation of domains. You see, so is it possible to find domains of such functions? Is it possible to find domains of such parametric functions? That's what we are going to look at right now. How exactly can one go about finding domains of such functions? You see, so let's look at domain. You see that. So let's first start by talking about this in 2D and see what we can say. So in two-dimensional space, you see that. So if you have the following parameterized vector function, which is in the form xt, yt, then one thing that you should know is that if you want to find what the domain of this function is, you see that, which I will write here as the domain of f arrow, then you should always know that the domain of f arrow is always given by the domain of the function xt intersecting the domain of the function yt. You see that? So which means the domain of any parameterized function is actually the intersections of the domains of the individual components, as you can see here. And this same thing also generalizes even in 3 dimension. You see that? So even if, let's say, I move on to 3-dimensional space, we still have the same thing holding true. So in 3D, nothing changes. So if we have our vector parameterized vector function ft, which is xt, yt, zt, like this, then the domain of f is just the intersection of the individual domains. So it is the intersection of the domain xt intersection domain yt intersection of the domain zt, like that. So that's how we actually find domains in these type of vector functions. So every time when you have a vector function like this one that we have here, then you can talk about how to find its domain by making use of these results that we have established here. You see that? So to do some practice on how actually we can go about doing this, let's look at the following examples. So a typical example that one can get will be as follows. You see that? So given the vector function, so we are given the vector function, which I'll define as follows, such that one of its components is root of t minus 1. And then the other one is arc cosine of 3t plus 1. Determine the domain of ft. So this is a typical question that you can get in an exam where you are asked to find the domain of a function like this one. So how can we go about finding the domain for a function like the one that we have below? How can we go about that? How can we find a domain for something like this? So to find a domain for something like this, at first we are going to extract the individual components from that. Because remember, every time when you have something like this, you know that the first component always stands for x of t, and the second component always stands for y of t. So we shall keep that in mind. Then now we'll see how to actually go about solving this problem. So we have what? So we have already that x of t is the function root of t minus 1, and also we have y of t, which is the function arc cosine of what? So let's go and cross check. It's 3t plus 1. So it's 3t plus 1. So these are the two individual functions that make up the components. Now, how can we find the domain of each of these? You see that? So to find the domain of each of these, now we know. You see that? So for xt, we know that. So from our understanding of the root symbol, we know that this t negative 1 that we have here must always be greater or equal to 0. So this implies t must be greater than 1 all the time. You see that? So that's what follows from here. So we can see now that the domain of xt is actually equal all numbers from 1 to infinity, like that. You see? Then now let's go to yt. What do you know about yt? So we see that yt, it is defined in terms of the arc cosine function. And you know that the arc cosine function can never give you a solution if this argument that sits here, so if this argument that sits here is not in the interval negative 1 to 1, we know that you can't get a solution. You see that? So every time, whatever the argument of the cosine function must be any number that lies between negative 1 and 1 for us to get an output. You see that? So what can we say from that? And for yt, we have that this 3t plus 1 must be an element of negative 1 and 1. So what this implies is that 3t plus 1 must be greater or equal to negative 1 and less than 1, which implies that 3t must be greater than what? Must be greater than negative 2, but less than 0. This implies again that t must be greater than negative 2/3, but less than or equal to 0. You see that? So which means we can now deduce from this that the domain of yt is what? It is all numbers starting from negative 2/3 going all the way to 0, like that. So now how can we then move on to find the domain of what we're looking for? So to find the domain of what we're looking for, we know that it is given by the intersections of these domains that we have calculated. So to find the intersection of these domains that we have calculated, how do we go about that? So the best way to do that is to always draw a number line and represent these two domains. So I've drawn a number line. So to represent the first one, which is 1 to infinity, we know that 1 can be a number which starts maybe here. Since 1 is included, our domain is everything from here to that side. Then to represent the other domain, we see that it's everything from negative 2/3 to 0. So the second domain is negative from negative 2/3 to 0. So negative 2/3 can be a number which starts somewhere here, and it ends at 0, which is somewhere there. So this is the interval. You see that? So we can see that already with these two regions that we have here, they do not overlap. So there is no point where these two overlap. So therefore, what can we conclude from here? So since there is no overlapping that is here, so therefore the domain of f that we're looking for, which is actually the domain of x intersecting the domain of y, is actually the empty set, because we can see that there is no intersection that is there. So there is no domain to this particular function. The domain is the empty set, you see. So which means there is no number that you can take for which both these individual components are both defined at the same time. So this is how we go about finding these things that are referred to as domain of parameterized functions. But let's look at also another example different from the one that we've seen. So another example that we have goes as follows. So this is a three-dimensional problem now. So given the function f of t to be equal to 1 over root of t squared minus 2 e to t, then a cosine of t minus 1, determine the domain of ft. So how can we go about finding the domain of this kind of function? You see that? So to proceed, this is how we go. So we have that. So we can simply see that in this case we have that x of t is equals to 1 over root of t squared minus 2. And also we have that y of t is equals to e to t. And also we have z to t, which is a cosine of t minus 1. So this is what we have now. So we want to see how we can find the domains of all these things. So to proceed now, this is how we proceed. You see. So first we look at x of t. You see that? So now what is x of t? We see that x of t is actually defined as 1 over root of t minus root 2 t plus root 2. You see that? So what exactly do we spot here? So we see that we have a combination of two things here. We have a root, and also the other thing that we have is a fraction. You see that? So to find the domain of this function that we have here, we have to consider two things depending on the nature of the function at hand. So we have a fraction and we have a root. So we have to ask ourselves, what do we know about fractions? You see that? So one thing that we know about fractions is that the denominator of any fraction cannot be 0. Do you see that? So from the fact that the denominator cannot be 0, it means we have to exclude all the t values that might cause it to be 0. So what do we see? So we can already see that t can never be equal to plus or minus root 2, because every time when t is plus or minus root 2, we have zeros in the denominator, which are things that are not allowed. You see that? So which means those two values are excluded. So the next thing that we have to establish now is we see that there is a root sign. So when is the root sign valid? You see that? So also we know that the root is valid is valid when what? So we know that the root is only valid when t minus root 2, t plus root 2 is greater or equal to 0. You see that? So this is now a quadratic inequality, and from high school we know how to find solution to something like this. So what we do is we draw a number line, and then we indicate these two critical values here in our number line. So we have the first critical value, which is negative root 2, and we have positive root 2. So we know now that in order to find a solution set for this problem, we have to first look at the three regions that we have created by drawing this number line, because drawing a number line allows us to create three regions. So if I can come and split here, you can see that we have three regions, which one is the first region, this one is the second region, and this one is the third region. So we know that some of these regions are the solution set that we're looking for. So to figure that out, we know how exactly we proceed. So what we do is we first look at the last region, which is region 3 in this case. And what we do at that point in time is we take any number that lies in that particular region. Like, for example, I can take the particular number to be 2. And if I take my number to be 2, what I do is I go back and place my 2 in each of these vectors. So if I place my 2 in each of these vectors, I see that they will both evaluate to a positive number. So if they both evaluate to a positive number, it means if I multiply those two positive numbers, I'll obviously get a positive sign here. Then once the region 3 has a positive sign, we know that all the other regions that follow, their signs must alternate from positive to negative, and then here to positive again. You see that? Now, if you look, the inequality is actually telling us that we're looking for a solution for which these two factors are both positive at the same time. They have a positive outcome. So when do we have a positive outcome? We can see that we always have a positive outcome at this zone and also at this zone. You see that? So which means now what can we say is the domain of xt? So this shows us that the domain of xt is actually all numbers from negative infinity to negative root 2 union from root 2 to infinity. You can see that I have already excluded negative root 2 and 2 because already from the top we had established that plus or minus root 2 is not allowed. So they have been excluded from being part of the domain of xt. You see that? Then, and what else? The next thing that we have now is yt. So yt, we know that is given as x to t, e to t. But we know that a function like this can take anything. You see that? So this implies the domain of yt is simple, all real numbers from negative infinity to infinity. Which brings us now to the next function, which is zt. So zt, we already seen that is defined as a cosine of t minus 1. So we know already from our discussion in the previous question that a cosine can only give us arguments when this thing lies in this interval. You see that? So from that, this is what we deduce. So we have that t minus 1 must greater or equal to negative 1 and less than or equal to 1. So from here we can see that t must always be greater than negative 2 but less than or equal to 0. You see that? So thus t must be an element from negative 2 to 0, which gives us the domain of yt. So therefore the domain of yt is what? It is everything from negative 2 to 0. So now I have to find the domain of the overall thing. You see that? So we know from our definitions already that we have stated that if I want to find the domain of f, it is just going to be the domain of xt intersection the domain of yt intersection the domain of zt, like that. So to find this, we have to at least do some illustration. So let's try to draw what we have. So the first domain that we have was from negative infinity to negative root 2, from root 2 to infinity. So let's represent what is going on. So the first set of problems, we have these things. So we have negative root 2 sitting here, and the solution goes all the way to that. And then we have root 2 where the solution goes all the way to that. Then the other solution takes the whole line because it's from negative infinity to infinity. Then the next solution that we have, it goes from negative 2 to 0. So if I were to draw it here, it will be from negative 2, which will be somewhere here, then to 0, which will be somewhere there. So we can see now, since these are included, this is the case now. We go from here all the way from here. So now let's see if we have an overlapping region in all these intervals that we have stated. So if you look close, you will see that in this zone, we have an overlapping region here. Because the pink is overlapping with the green line, it is overlapping with the black line. So this is the region that is common to all the three intervals. So therefore, this must be the domain that we are looking for. So therefore, what we can conclude now is that the domain of our function f of t is simple numbers starting from negative 2. So if you look, negative 2 is included, so it's negative 2 with a square, but to negative root 2, so to negative root 2, but which is excluded. So that forms the domain to our problem. So this is how we get to find domains of these multivariable functions which are parameterized. Otherwise, I will stop this lesson here. And in our next session, we are going to look at how to find the limit in situations like these, where we have parameterized vector functions, and we want to introduce the notion of the limit on these functions. Otherwise, thanks for watching, guys. I'll meet you on our next